The harmonic oscillator is a very typical toy system in which a potential energy quadratic in space is assumed for a particle. When does this ever occur in nature, I hear you ask? Imagine you have some general potential wobbling through space and that this potential has a stable minimum somewhere. In a classical system, this could be a spring that is expanded or compressed. A quantum mechanical version is, for example, an atomic core in a periodic crystal lattice. If we assume that the particle sits at the minimum or is excited only a little bit around it, then we can approximate the potential energy using a Taylor series. The force acting on the particle is given by the derivative of the potential energy. But this means that if the first coefficient does not vanish, then there is a force acting on the particle when it is sitting in the minimum, making it, well, not a minimum. We can therefore conclude that the first non-vanishing term in the Taylor series of a potential energy around its stable minimum is quadratic and hence resembles a harmonic oscillator. So yes, they don't really occur in nature, but they are very often a good approximation. We can now write down the Hamiltonian for the oscillator and, because we already know the classical solution, write it in terms of the classical oscillation frequency omega. Because I know where this is going, I will define a new operator A as a prefactor times the position plus I times a scaled momentum. Note that A is not a Hermitian operator and hence does not correspond to a measurable quantity. We can use the operator and its Hermitian conjugate to rewrite the Hamiltonian. When multiplying out the two terms, you have to be careful because, remember, x and p do not commute. Their commutator does come up though, and we can plug in the result that we already know. Comparing this result with the Hamiltonian, we find that it is given by h bar omega a dagger a plus h bar omega over 2. This is a really nice and simple form, but does it help us? In order to find out, it's useful to know the commutator of a and a dagger. It can be calculated using the already known commutator of x and p, and turns out to simply give 1. We now know what is left over if we change the position of a and a dagger. Now let's imagine we have some eigenfunction phi of the Hamiltonian which has some energy E. We want to find out how the Hamiltonian acts upon the wave function a dagger phi. With the help of the commutation relation, we can pull the a dagger operator to the front. What's left is the Hamiltonian plus a new term h bar omega. Because phi was assumed to be an eigenfunction of the Hamiltonian, we can replace the operator with e. Now only numbers are left, and we can push a dagger safely back to the wave function. What we observed here is that a dagger took an arbitrary eigenfunction of the Hamiltonian and created a new one, whose energy differs by the value h bar omega. Similarly, A constructs an eigenfunction whose energy is h bar omega lower, as you can easily verify. However, there has to be a ground state with lowest energy. Acting with A on the ground state should give us 0. Plugging in the definition for A gives you a differential equation which is solved by a Gaussian curve. If you now explicitly calculate the energy of this wave function, you find it to be h bar omega over 2. I suggest that you do those calculations yourself. The energy of the nth eigenstate is consequently given by n plus a half times h bar omega. It is because of this that a dagger a is often called the number operator. It is interesting to note that the ground state does not have energy 0, while a classical particle can just rest in the minimum. This so-called 0-point energy came along because x and p refuse to commute. Watch the video again if you don't know what I'm referring to. In fact, this points to a very fundamental concept in quantum mechanics, which will be covered in the next video. Until then, enjoy life if you can, and don't be ashamed if you can't.